Hello everyone, I welcome you all for the today's session. Today's session is all about a quick sort. So before moving into the contents, let me introduce myself. I am Lakshmi Vaibhavi NV, currently pursuing BE in CSC AI at SVC. So let's get into the topic. Here we are with a table of contents. At first we'll be looking into the introduction to the quick sort, then analysis of the quick sort algorithm, then time complexity of the quicksort like best case, average case and worst case, then a quick example of the quicksort implementation. At last we'll be having benefits and limitations of the quicksort. So before quicksort, let me tell you about a sorting. What is this sorting? The arrangement of data in a preferred order is called as sorting. This preferred order, I could say, let it be in an ascending order or descending order, or it can be based on the alphabetical wise also. So the next question is why sorting? So sorting makes many questions about the list easier. Like if you have a list of elements and you want to find some element, like if it is in the sorting order, it makes us to easier to find out that element within a short duration of time, right? So this is why we need a sorting. So here are some sorting methods I have listed down here. Here are bubble sort, merge sort, quick sort, insertion sort, then selection sort, binary seed sort and much more, but I have listed some of them here. So what is quicksort? Quicksort is an algorithm based on a divide and conquer rule. What is this divide and conquer rule? So divide and conquer rule is probably the best general algorithm design technique, and here are the general plans. A problem instance is divided into several smaller instances of the same problem, ideally about the same size. So if we have a list of elements and we are going to divide it in a equal size, then a smaller instance is solved. Then if necessary, the solutions are obtained for the smaller instances are combined to get a solution to the original solutions. It's nothing but if we have a list of elements and we are going into, like we are dividing into a two list of the same order, then we are going to sort that order, then we are going to combine it back to get a solution. This is what a divide and conquer. So this rule is implemented in the quicksort. Then an element will be selected with respect to whose value we are going to divide the array. This element is called as a pivot. As I said, the pivot element is the one element. Based on that element we are going to sort this, like we are going to divide the array. So usually the pivot will be selecting to find out the pivot element, will be starting from the beginning. So about this pivot we'll getting to know when I take the examples. Then this comparison is based on recursive sorting algorithm. Why is recursive? Because until we'll list down the array in the sorted order, we will be calling the same function, we will be doing the same thing. So this is called as, so this is why this is recursive sorting algorithm is used in a quicksort. So the next thing is selection of the pivot. When the collection is sorted, choosing the pivot as the mean of the collection results in the best case running time for the quicksort algorithm, because the mean element is close to or equal to the median element, which divides our collection into equal halves in each recursion, whereas choosing the mean of an unsorted collection of the element gives a mean, which when chosen as a pivot element will partition our collection into skewed part and consisting of 1 and n minus 1. So here the best case of this is big O notation n log n, and worst case is big O n square. Then the steps, like general steps how we are going to implement this algorithm. At first we'll be choosing a pivot element. Selection of an element from the array to serve as the pivot. The choice of a pivot can vary, but a common approach is to select a first or the last element. Then partitioning, as I said, it is a divide and conquer. Rearrange the array so that all elements smaller than the pivot will move to the right, and the element which are, like if you consider one element, the left side of the element will be having a elements which is smaller than that element, and at the right side will be having a greater elements. Then recursive calls, after partitioning you have sub-arrays, one with elements smaller than the pivot and another elements greater than the pivot. Recursively applying the same partitioning process to each subarray. This means selecting a new pivot for each subarray and repeat steps 2 and 3 until the subarrays have size 1 to 0 and the subarrays are considered sorted. And you will be repeating the same steps until the list is in a sorted order. So here is the quick example of this quick sort. So before that we'll be seeing the algorithm for the partitioning. So you'll be choosing A of like beginning when I is equals to 0, when the index value I is equals to 0, that first element will be considered as a pivot, and you'll be repeating the same step. What you're going to repeat the same steps means how we are going to swap. See, you'll be incrementing the I until you find A of I is greater than pivot, and you'll be incrementing the j. I mean, you like from like I could say it is not incrementing it, you are going to decrementing the j until you find A of j is less than of pivot. So getting back to the example, see, consider here. So let me consider this thing as a pivot. A of I means A of 0 is 70 and A of j, that is n minus 1, it will be a n. So just had given like had given here start and end here, so to make it easier. See here, is this A, so considering this pivot, is A of I is greater than or equals to pivot? No, it is less than or equals to pivot. Now we are going to increment this thing. So is 60 is greater than pivot? No, again increment 100. So the at start will be coming to the here, then so you want to stop it here and end. So is A 70 is less than or equals to here, A of j should be less than or equals to pivot. Yes, so this 70 is less than or equals to pivot. It is not less than, but it is equals to pivot. Now what you are going to do, you are going to swap it. See here, the 70 comes into the place of 60 and 100, and 100 moves to the place of the end. Now again you are going to going to start the same steps. Now the start is at 70 and you are going to increment this. Is 50 is greater than 70? No, you are going to increment. Is 90 greater than 70? Yes, you are going to going to stop here. Now A of I is at 90 and before we had A of j at 100. Now we are going to increment. So 150 is less than or equals to pivot? No, it is greater than pivot. Now 10, is this less than or equals to pivot? Yes, it is less than or pivot. Now we are going to swap. So 10 moves at a place of 90 and 90 moves at the place of 10. Now again you are going to start. Start is at here at a 20. Start is at 10 and stop is at 90. Is 20 is greater than or equals to pivot? No. Then you are going to increment. 90 is greater than pivot? Yes. So here of I will be at the 90. Then 150. What we need? A of j should be less than or equals to pivot. 150 is less than or equals to pivot? No. 90 is less than or 70? No. Then 20. Yes. This end comes here. Now we are going to swap it. No, you should not do the swapping because A of j has been, it has crossed over the A of I. Now you are going to stop your sorting. You are going to stop at the place of the end. At a place of 20, you are going to shift swap the pivot element. That 70 comes here. So at last we have find out the listed order. Means, see, at the left of the 70 you had find out the elements which are less than the 70 and at the right side which is greater than the 70. This is what the steps we are going to do. Again you are going to do the same steps until you find out that each and every element is in the sorted position. This is what a quick sort. See here, the same thing has been given in the algorithm. So you are going to swap until you find A of I is greater than P and A of j is less than or equals to P. So until you are going to do this, until where? When I is greater than j. So here you can see when I is greater than j, at this step you have find out that I has crossed over the j and j came before the I, right? So there you have stopped your sorting and you had given the place for the 17 as a pivot element. This is the algorithm. Then coming into the time complexity, the amount of time taken by an algorithm to run as a function of the length of the input, this is called as a time complexity. The time complexity here, the first thing is best case. The best case time complexity is big O notation n log n. When the best case occurs, it occurs when a pivot selection always chooses the medium element, resulting in perfectly balanced partitions at each recursive steps. When you find out, when it comes to the middle of the sorted, in a middle element, when you are choosing as a pivot, that time you can find out the best case. Next, this is the steps you can go through the how it has been solved. Then coming into the average case, when the array elements are jumble order and it is not in a properly ascending and not properly descending, this popular sorting algorithm has an average case performance of theta and log n, which contributes to making its very first algorithm in practice. So the best case, at last, the time complexity of the best case is theta of n log n, big O n into log n. Then comes the worst case. Worst case is that when, see, like for example, you cannot find here 80, right? So when the element is not at all in an order, or it occurs when the pivot element is either the greatest or the smallest of the element of the array. Suppose that the pivot element is always the last element, it would occur when the given array is sorted already in an ascending or an descending order. So the time complexity is big O notation n power 2 n square. So this is the worst case. Then conclusion. Usually these worst case, all splits will be skewed in the extreme and one of the two subarrays will be empty, while the size of the other will be just once less than the size of the subarray being partitioned. Then at last, conclusion, why we need a quicksort. Quicksort is widely known for its efficiency in most cases. Its time complexity helps in assessing its performance and optimizing it for better results. As the name only indicates, the speed of the quicksort makes it one of the most important algorithms. It can be applied to files of any size. Reading of the input during the run creation step is sequential, and it is not much seeking also. There's not much steps to be done here. Then thank you guys, that's all for the today's session.